Hello everybody, myself Prashant Mukhopadhyay, faculty member Electrical Engineering Department, Greater Kolkata College of Engineering and Management. In Power Electronics and Drives class, we have so far covered up to Unit 4, and in our last class we were actually discussing about this DC choppers, and in the last lectures we have discussed about the load commutated choppers, that is Jones chopper. Okay, so before that actually we have covered the entire, more or less the entire syllabus up to Unit 4 of this Power Electronics and Drives course, and where we have seen that is from the very beginning, that is power semiconductor devices, its thyristor, its construction, operation, symbols, and not less than that. So we have also discussed about diag, track, SCS, IGBT, then switching and timer circuits in Unit 2, and different multivibrator circuits using say op-amp as well as IC 555 timer circuit. And then we have in Unit 3 we have covered the converter and inverter part. Also we have covered cycloconverter, and then in Unit 4 we have discussed about the DC chopper. So different choppers, step up, step down, and different type of say choppers A, B, C, D, etc. Different choppers and commutation methods of choppers and auxiliary commutations, load commutation, etc. So today actually we'll start a new unit, that is the last unit of this say course. So that is Unit 5, and that is DC and AC types. So here we will discuss different speed control methods of DC motors, AC motors, then actually say UPS, etc. So speed control will include both separately excited say single phase fully controlled converter, three phase fully controlled converters, then DC series motor speed control, DC servo motor, then three phase induction motors in case of speed control of the AC motors. So particularly three phase induction motor with variable frequency PWM DSI, voltage source inverters, and then speed control of three phase induction motor with a variable voltage and variable frequency control, VF control, and then speed control of AC servo motor, and then static power compensation systems, its operation, block diagram, UPS, and its operation, block diagram, etc. So we'll one after another we'll cover it. So let us see up to what extent we can say discuss in today's class. The application of power electronics, basically literally it is impossible to list all the applications of power electronics today. So it has penetrated almost all the fields where electrical energy is in picture. So this trend is an ever increasing one, especially with the present trends of new devices and integrated design of power semiconductor devices and controllers. So this ease of manufacturing has also led to availability of these devices in a vast range of ratings, and gradually has appeared in high voltage and extra high voltage systems also. And the day is not very far away when all of the electrical energy in the world will pass through the power electronic systems. So with this introduction, we can give you a picture of the applications of the power electronics. So we in the say below our diagram, we are say actually attempting to briefly present the diaspora of power electronics. If you see, if you go to this application of the power electronics field, so this is while it is not extended, if we say in this way. So it is extended into automotive and traction. It is extended in industries, renewable energy, defense and aerospace, utility system, and also in our daily life. So if we say just give you a overview of these applications of power electronics and say different fields. So and we will take it one after another. So automotive and in traction. So you can have, say, in case say modern traction systems, seats, electric power steering, then showers, then hybrid electric vehicles, forklifts, etc. In industries, we are using power electronics in rolling mills, elevators, pumps, cement mills, construction machineries. In renewable energy field, we are using power electronics in wind system, solar system, and in say our daily life, we are using power electronics in vacuum cleaners, UPS, computer, air conditioning, etc. And in utility systems, we are using power electronics in smart grids, facts, HVDC transmissions, and defense in aerospace. So particularly, we are using the satellites, space shuttles, aircraft, etc. Cannot be think of without the applications of the power electronics. So if we give you a gist or give you a small light of this vast area, so actually, while we are not using this power electronics in our daily life, we are using the power electronics applications in fan regulators, in light demand, in air conditioning, induction cooking, emergency lights, personal computers, vacuum cleaners, UPS, battery chargers, etc. In automotives and tractions, that is subways, hybrid electric vehicles, trolley, forklifts, and many more. Modern car itself has so many computer components. Power electronics are used, such as ignition switch, windshield, wiper control, adaptive front lighting, interior lighting, electric power steering, and so on. So besides power electronics are extensively used in modern traction system and ships. So in industries, almost all the motors employed in the industries are controlled by power electronic drives. As for example, rolling mills, textile mills, cement mills, compressors, pumps, fans, blowers, elevators, etc. And rotary kilns. Other applications include welding, arc furnace, cranes, heating applications, emergency power systems, construction machinery, excavators, etc. And defense and in aerospace power supplies in aircraft, satellites, space shuttles. So advanced control in missiles, unmanned vehicles, and other defense equipment. So renewable energy field also generation systems such as solar, wind, etc. need power conditioning systems and storage systems and conversion systems in order to become usable. So for example, if we think about solar cells as DC power, and for generation applications we need AC power, and hence power electronic converter is used. And in case of utility systems, suppose in HVDC transmission, in power compensation, that is static say voltage SVC, static circuit breakers, generator, etc. systems, facts, smart grids, etc. we are using power electronics. So today actually we will say confine ourselves our discussions with as we have been guided, or we have been stated in our curriculum. So that is firstly speed control. So speed control of AC and DC motors. So we'll start with speed control of the DC motors. So basically, you know, the DC motors are used extensively in adjustable speed drives and position control applications, and their speeds below base speed. It can be controlled by armature voltage control. And everybody, you know, those who have studied minutely the electrical machines, so you know the speed below base speed can be controlled by armature voltage control. If you go to the characteristics of the DC motors and its equations of the speed equations, you will find that below base speed can be controlled by armature voltage control. The speed above base speed are obtained by field flux control, basically flux field awakening method. And as speed control methods of the DC motors are simpler and less expensive than those for AC motors. So DC motors are preferred, and a wide speed control range is required. So the DC motors used in conjunction with power electronics converters are DC separately excited motors or DC series motors, and depending upon the type of AC source or the method of voltage control. So DC drives are classified as either single phase DC drives and 3-phase DC drives and chopper drives. Okay, so with the advent of power electronics in the industry today has changed the scene completely, and direct current motors or DC motors have been used in variable speed drivers for a long time. The versatile control characteristics of DC motors have contributed to their extensive use in the industry, and the DC motor can provide high starting torque, which is required for traction drives, and control over a large speed range, both below and above the rated speed, can be easily achieved. So the methods of speed control are simpler and less expensive than those of the alternating current motors. So if we go to the discussion, so we'll find this two figures 1 and figure 2, where the block diagram of a typical powerful electronic systems and thyristor DC drives and frequently require sophisticated control systems, and both analog and digital feedback controls are used, and phase locked loop control techniques are employed in some DC drives to provide speed control and essentially zero speed regulations. Microcomputer control of complex drive systems can provide so great operating flexibility when required. So there is no wonder that today this technology is well understood and proven, which say resulted in its popularity in the world over. So this is actually the block diagram of the typical power electronic systems. We have already discussed this power electronic system at the very beginning of this say power electronics discussions and its application of drives, so power electronic drives also. So basically this is power electronic circuit, and this will say supply to the load, the output is supplied to the load. And before, so this power electronic circuit is being controlled by digital circuits, and it's a digital circuit, so which is a part of the say, control unit, and control unit will be response when it is given a command, and this command will be further modified with the feedback loop, so speed sensors, and it is when this feedback signal say by this say speed sensor will goes to the command, this either signal or this compared signals will be supplied to the control unit, and so this control unit as a whole will control the digital circuit, and that will control the power electronic circuit, and hence the output, the desired output will be provided to the load. So this is the typical block diagram of power electronic system, and this is actually we have discussed in the very beginning of our this course discussion. And in the figure 2 we have classified as a different regulated power supplies. Say power supply definitely is the heart of say of any electronic systems, and since electronic components are sensitive to voltage, the power supply must provide regulated voltage to the system for satisfactory performance. So an ideal regulated power supply is an electronic circuit that provides a predetermined DC voltage as output, and which is independent of. An ideal regulated power supply is an electronic circuit that provides a predetermined DC voltage as output, and which is independent of say the current drawn by the load, and any change in the input AC line voltage, that is RMS voltage, and any change in temperature of the components and ambient. So this is a ideal regulated power supply, definitely an electronic circuit, and it's provide a predetermined DC voltage as output, and this is independent of the current drawn by the load, and any change in the input of AC line voltage, that is RMS value of this AC line voltage, and any change in temperature of the say components and ambient. So basically say with this actually we are showing this in the classification of this regulated power supplies, as I told you in the figure 2. So this is the regulated power supply. So this is generated voltage regulators, and this is linear regulators, which again can be subdivided into shunt regulator and series regulator. And third one is this switching regulators, which may be subdivided into PWM mode, switch mode, and resonance switch mode. So far we have discussed all these things. And in PWM switch mode, we have discussed about this buck regulator, boost regulator, buck booster regulator, and cup regulators. So these portions actually so far what we have discussed, so that is being summarized, particularly this regulated power supply portions, and as well as this how this power electronic systems operates. So this is at the very beginning we have discussed. So once again I am repeating it so that we can say in the applications part we can get say recognize this, remember this systems applications. And one more thing is that this regulated power supply, so that also we have discussed. This regulated power supplies may be generator voltage regulator, and it may be linear regulator, that is shunt or series regulator, and in the most important one, the switching regulators, which again subdivided into PWM switch mode and resonance switch mode. That portions we have covered in the last unit itself. So, and this PWM switch mode, we are having buck regulator, boost regulator, buck boost regulator, and cup regulator. So everything these portions we have covered in say our previous defined units, inverters, then resonant pulse converters, etc. portions. So with this introductions of this application part, we will try to discuss the different methods of the DC motor speed control. So methods of DC motor speed control, and the speed of a the DC motor has to be controlled from an AC or DC source. Okay, and the two basic methods of the DC motor speed control is shown in this figure. So figure 3. So actually this speed control of the DC motor we will discuss in details, and this is more common where control rectifier is used. So this in figure 3 is more common where control rectifier is used to supply the motor armature. And the most common form of variable speed DC drive is based on the control of armature voltage, and hence the motor speed is dependent on the firing and delay angle of the rectifier. Okay, that is alpha. So the speed of the motor is driven by its say mean armature voltage, any oscillating torque produced by the harmonic voltage components being heavily damped by the motor inertia, and say if required, the field can be supplied by a control rectifier, and where the machine is required to generate, if rapid braking is required, then converter must be capable of operation in the inverting mode. So this is basically the methods of DC motor speed control, and say this is the actually diagram. So basically this is DC motors, and this motor is this is the DC voltage. So basically this is chopper, DC converter. So from fixed DC we can get this variable DC which is being supplied to the armature, so of the DC motor. And see, this is the speed sensor, basically speed sensor. So this is given to the summing device or say comparators. So this is the reference speed, and this is the speed, and this output is being fed back to here. This comparator will say generate the result of this after comparison. So this is the reference and this feedback signal, and this is the speed controller. So which will then this is the current sensor, so that will control the given to this speed controller, and this is the armature current. So this armature current is in this portions will be the signal, error signals will be given to the current controller, and that will give you the required delay angle, so firing angle for the chopper circuit. So that is thyristors. Okay. So basically, this is the speed control say diagram of DC motor. So one after another we will discuss this single speed control mechanism with the help of the power electronics applications. Now first of all we will discuss about the single phase separately excited drives. So this is actually phase control DC drives applications. In phase control DC drives and AC to DC phase control converter is used. This is AC supply, and this is actually output DC. This is actually the freewheeling diode or the diode protection purpose. So this actually it is single phase separately excited say DC drive, and this is single phase separately excited drives circuit diagram, and we have already discussed about this phase control converter. So this phase control AC to DC converter is used to control the DC drive motor, and control rectifiers to for DC drives are widely used in applications requiring a wide range of speed control and frequent starting, braking and reversing. And some prominent application, as I told you, are in rolling mills, paper mills, printing mills, say mine winders, machine tools, etc. And so this is circuit diagram. Basically this is the motor, so a DC motor, and this is its field. It's a separately excited field basically. So single phase separately excited DC drives circuit diagram is like this. Okay. Now this converter is used for a particular application, depends on such factors as the supply available, rating of the drives, amount of voltage able to be tolerated, reversible or non-reversible drive, need for regeneration, etc. And the basic circuit arrangement for a single phase separately excited DC drive actually shown in this figure 4, and the armature voltage is controlled by semi-converter or full converter, and the field circuit is fed from the AC supply through diode bridge, and the motor current cannot reverse due to thyristors in the converter. So basically this is this output actually say this is field. Okay, this is field here, and supplied by say diode bridge, and this is say for armature voltage. Okay, so this converters is used, this single phase separately excited drives and mostly widely used in say rolling mill, paper mills, printing presses, mine winders, machine tools, etc. Because speed is very important here. So say if the speed is not constant, so the product of where it is being used will not be of say required level, of required level. That is, it may be thickness, it may be productivity, whatever may be the case. So that should be controlled by the say drives itself. That is the speed by controlling the motor speed. Okay, and here two parts are there. So one is the field, and this is separately excited, and this is supplied by this diode bridge, and armature voltage is being supplied by this semi control converters. Okay, so from AC to DC, this output voltage is being supplied to the armature voltage for the controlling the speed of this separately excited single phase drives. Okay, so I think you got the application part and the idea, basic idea why it is being used, and So this is very important. Say, and this applications is widely used in this particular field of this sector. So industries and rolling mills, paper mills, printing presses, manuators, machine etc. Okay. Now single phase half wave converter drives. So it is you see this is the half wave converter drives. Okay, and this is the single phase half wave converter types waveform. Okay, basically this portions we have already discussed when we have discussed about the single phase half wave converter types. So here only we have replaced the load by this DC motors, separately excited DC motors. Okay, so half wave converter for controlling separately excited DC motor. So this is their circuit diagram, and this is the waveforms, and it requires a single thyristors and a freewheeling diode. This is the freewheeling diode, and in this circuit the motor current is always discontinuous. You see, this is the output current, and this is always discontinuous. Okay, so discontinuous in nature. So resulting a poor motor performance, and this type of controller is employed only for motors below say 400 watt. Okay, and then single phase full converter drive, and a full converter feeding separately excited DC motor, and in the full converter system thyristor TU11 and TU13 are simultaneously triggered at alpha. Okay, CPC T11 and T13 simultaneously triggered. Okay, and see and this is triggered at a delay angle alpha. Okay, so this is triggered at a delay angle alpha. Clear? So this is the firing angle, and then thyristor T12 and T14 are triggered at pi plus alpha. Say these two T12 and T14 are actually triggered at angle delay angle pi plus alpha. So this is here. Okay, so with this and this basically voltage and current waveform under continuous and current conductions are shown here. So in these two figures. Okay, the motor is always connected to input supply through the thyristors. See, connected to the input supply through the thyristors, and the thyristor T21 and T23 conduct during the interval say alpha to pi plus alpha, and connect the motor to the supply. Okay, show here. Okay, so T21 and T23. So, and a full converter is a two-quadrant converter. Basically, it's a two-quadrant converter. So, and in which the voltage polarity of the output can be reversed, and but current remains unidirectional because of the unidirectional thyristors. And if the motor back EMF is reversed, it will behave as a DC generator and will feed power back to the AC supply. And this is known as the inversion operation of the converter, and the inversion mode of operation is used in the regenerative braking of the motor. So this two-quadrant operations is required for say the purpose to fulfill this say output voltage polarity can be changed or inverse or reverse, but since it is the unidirectional thyristor being used, so current remains unidirectional, and if the motor back EMF is reversed, so it is known as the inversion operation of the converter, and the inversion mode of operation is used in case of the regenerating braking of the motor. Okay, so and then we'll discuss DC chopper drives. And chopper circuit is used to repair the numerous types of electronic switching devices and circuits, control of a DC motor speed by a chopper is required, but the supply is a DC or an AC voltage that has already been rectified to a DC voltage, and the chopper may be thought of as an AC transformer. So since they behave in an identical manner, and chopper control DC drives also have applications in servos, in battery operated vehicles such as forklift trucks, trolleys, and so on. And the chopper is a static device that converts fixed DC input to a variable DC output voltage directly. We have already discussed, and choppers are used for the control of DC motor because of a number of advantages such as high efficiency, flexibility in control, lightweight, small size, quick response, and regeneration down to very low speeds. And the choppers offer a number of advantages over a control rectifier for a DC motor control in open loop configuration. Reductions or eliminations of discontinuous conduction region improves speed regulations and transient response of a drive. The most important applications of choppers are in the speed control of DC motor used in industrial or traction drives, and because higher efficiency frequency of the output voltage ripple, the ripple in the motor armature currents is less, and the region of discontinuous conduction in the second and the speed torque plane is smaller. Reduction in the armature current ripple reduces the machine losses and its de-rating. So this is chopper drives is shown here. So this is chopper drives, and this is the waveform. So in a say quick way, so we have discussed about this DC motor speed control with the help of the power electronics. So power electronic devices. So that is, we are using here say phase control rectifiers. We are using here DC to DC converters or choppers for different specific applications of the DC motors to get our required output level or speed to match our requirement. So I think in these discussions you will have say quick idea about this application part of the power electronics, particularly in the speed control of the DC motors. And whenever you will go to the industry or in your practical say application part, so you will be able to match this say learning of power electronics and its applications in different say area, particularly in industry where it is extensively or widely used. And in details we have discussed all these devices. Only we have and we have also discussed these devices with the different types of load, RL, RLC, RLE, whatever be the cases, and that's say knowledge is being applied here. So thank you for patient hearing. So,